I talk about quantum stuff so much, sometimes I think I should just rename this channel to Quantum Chronicles with Sabine. It's not just because of my personal interests. There really is a huge amount of research on quantum anything at the moment, and most of it is worth the excitement. We've only just begun to explore how quantum effects can be used for better computation, more precise measurements, custom-designed materials, and much more. And then there's the quantum internet, a solution in search of a problem. Let's have a look. The quantum internet is the idea that we'll send around quantum information across the globe through fiber optics cables or to and from satellites. That it works with quantum information means it can maintain fragile quantum links, which are called entanglement. A lot of countries have invested heavily into this new technology, including the US, the European Union, and especially China, which wants to put an entire quantum network into space. Oh dear. Why would you want to do that? Yes, that's a very good question. Before I say anything more, I need to clear up the myth that a quantum internet would be faster than light. This myth can be found on the pages of Nature magazine and in other places. It comes from the widely propagated but wrong idea that if you do something to one of a pair of entangled particles, the other one changes instantaneously. But this is just wrong. Yes, entanglement is a link between two quantum particles, and yes, that can be non-local, but it's just a correlation between the properties of the particles. It's not a physical link. Let me give you an example. If I break a cookie into two halves, then the exact breaking patterns will fit together. The patterns are correlated. If you know one, that tells you something about the other. If I put one half of the cookie on the one side of the desk and the other half on the other side, I now have a non-local correlation. Quantum entanglement between two particles is like that. The correlation between their properties, say spin, is locally created, but then you send one particle one way and the other particle the other way, and they'll still be correlated. Now, if I turn one side of the cookie over here, what happens to the other half? Nothing. It's the same with entangled particles. If you do something to one of the entangled particles, what happens to the other is exactly nothing. It's not all that difficult to understand, is it? But I've seen even physicists getting this wrong. I believe the reason for this widespread confusion is that entanglement is frequently and erroneously referred to as Einstein's spooky action at a distance. However, it's not what Einstein meant by spooky action, because there's no action in a correlation, and Einstein wasn't exactly dumb, was he? What Einstein meant with spooky action is the supposed collapse of the wave function. That, however, is unobservable, and since it's unobservable, you also can't send any information with it. That it's unobservable is also why Einstein thought it's not real, but that's another story. Let's come back to the quantum internet. So the quantum internet will certainly not be faster than the speed of light, and indeed that's not the reason countries are investing into it. I believe the major reason for these huge investments is that physicists have somehow managed to convince the military or intelligence organizations that they need a quantum internet to keep data safe. Partly this was based on another myth, which is that quantum computers will be able to break all encryption protocols. However, I think by now governments have understood that this isn't true. There are encryption protocols which are safe from hacking by quantum computers, and the transition to those quantum-safe encryption protocols is underway. But it's true that sending information with entangled particles would be ultra-secure. That's because if you send a message with entangled particles and someone measures one while it's on the way, that'll change it, and that will erase the message. Not only will they not get the information that they wanted, but the intended recipient will know that someone tried to intercept the message. And that's all well and good, except that measuring a quantum state doesn't mean you need a big detector or anything. A measurement is really any sufficiently strong interaction that causes causes decoherence. And this means that even small disturbances on the way of your quantum message will prevent the message from arriving. Does that sound like a practical method of data transfer? It's not what it sounds like to me. To deal with the fragility of the quantum message, you need to very carefully prepare it, which takes time, and then you need to send many copies of each bit of information. The consequence is that the bandwidth of the quantum internet is and will remain miserable, especially from and between satellites. You can't transfer any sensible amounts of data with this in the foreseeable future. Maybe you could use it for some kind of brief authentication protocol or key sharing. But then what? It's not that I think it won't work, I just think that it will be too cumbersome and expensive. I find it very curious that while quantum computers have gotten so much fire for being hyped, the quantum internet has far less promise, but no one ever says anything about it. Though I guess someone just did. The other day, I read on the BBC pages that CERN will look for ghost particles and that, quote, scientists think they found a way to prove whether or not these ghost particles exist, end quote. I know you expect me to say it's all bullshit, but I must disappoint you. I think it's a good idea. Let's have a look. At first, I thought the article was about what particle physicists call ghosts. These ghosts are mathematical structures that they use in some models to avoid problems with the calculation. But these ghosts are not what the CERN experiment is looking for. It'd be pretty crazy because you can't measure them. They're not real. That's why they're called ghosts. My second thought was that this is a weird way to say they're looking for particles called neutrinos, because the popular science press often refers to them as ghostly. That's because they just go through everything. Yes, neutrinos also go through you as we speak, at a rate of about 100 trillion or so per second. The vast majority of them come from the sun, though if you have a nuclear power plant near you, maybe you get some from there too. A little hello from your neighbor plutonium. Neutrinos are not what CERN wants to look for either, though. My third thought was that it's a spin on this other story about ghosts at CERN, but that turned out to be about something else entirely, namely resonances of bound states. My fourth thought was that they seem to have a lot of ghosts at CERN, and maybe they should do something about it. Finally, I figured out that the BBC was writing about a new experiment called Search for Hidden Particles, SHIP. That includes particles which could make up dark matter or dark energy. This experiment has been in the planning for about 10 years or so, and the news is that it got the go-ahead. And no, it's nothing to do with the bigger collider that they hope to build. It actually won't even use the Large Hadron Collider. Instead, it'll use a proton beam from a different accelerator at CERN, the Super Proton Synchrotron SPS for short. The SPS is the pre-accelerator for the LHC, the opening act, so to speak. It reaches a fairly low energy of about 5 GeV. The new SHIP experiment, so the plan will use the SPS beam, but not for head-on collisions, but to dump it into a target made of tungsten cladded with tantalum. These are two of the heaviest non-radioactive elements. The point of doing this is that while these collisions with the target will be of much lower energy than those between the proton beams at the Large Hadron Collider, it'll make many more of them. So if there are any particles that are fairly low energy but are produced very rarely, that's the way to look for them. This experiment makes sense because some of what I'd call the most plausible dark matter candidates are of the sort that they could find. Yes, dark matter may not exist, but if it does exist, then in recent years the evidence has noticeably shifted from fairly massive particles that they looked for at the LHC but didn't find, to very light particles or axion or those making up fuzzy dark matter, which the SHIP experiment could find. The major reason for this shift is that these particles all have quantum properties, meaning they are also waves. And the lower the mass of the particle, the larger its wavelength. For particles of masses so low that the SHIP experiment could find them, the wavelength can be the size of galaxies. Yes, Crazy stuff, but true. This is interesting because that way we could get noticeable quantum effects in the dark matter stuff that solve some problems. For example, they prevent the density in galactic cores to come out higher than observed. This is a typical problem for dark matter made of heavy particles. If the particles are light enough, quantum uncertainty avoids that. The equipment of the ship experiment has been in trials for several years. It's supposed to be completed in the next 5 years or so, and then to start running around 2030 or so. It'll of course not, as the BBC wrote, prove whether or not those ghost particles exist, because you can always say they're just a little more weakly interacting so that we haven't seen them. Then again, the experiment is not super expensive, costing just about 100 million euro, and it's making use of an already existing machine, and it's probably one of the least expensive ways to look for a whole lot of particles, so... But could you please stop calling them ghosts? Physicists are about to launch a new experiment at the South Pole to try and figure out whether space has quantum fluctuations. They just concluded checks on their equipment and found that it works as desired. Next, they'll do the real thing. And you know what? They do have a pretty good shot at finding something. Let's have a look. Most physicists think that space should have quantum fluctuations. But if you think of those fluctuations like tiny little ripples, think again. They'd not be tiny ripples, they'd be wild, because in quantum physics, everything that can happen does happen. These quantum fluctuations of space could do everything. Tiny black holes, wormholes, they could even make new baby universes. The stuff is called quantum foam, and the reason we don't notice it, so the idea is that these wild fluctuations are just too tiny and fast. But physicists believe that something like this is necessary to solve one of the biggest problems in physics, if not the biggest one: how to combine Einstein's theory of gravity, that's general relativity, with quantum physics. Albert thinks his theory is good as it is and all that quantum stuff is nonsense. However, most physicists disagree. They think that we need a theory of quantum gravity. And the most basic expectation you can have of this theory of quantum gravity is that space should have these quantum fluctuations. But space is the thing that particles move in, and so those quantum fluctuations of space should affect how the particles move. Just how that happens depends on the details of the theory. Jonathan Oppenheim, for example, thinks that these space-time fluctuations should induce the collapse of the wave function. And that may or may not be correct. But generally, you expect that the quantum foam affects particles more the longer the particles travel. This is why there have been a bunch of experiments that look for distortions in signals from very distant sources. And when I say very distant, I'm not talking about your fifth cousin John. I'm talking about billions of light years. Particles that have literally crossed the entire universe. Several experiments looked for it, and you already know that they didn't find anything, because otherwise you'd have heard of it. For this, one usually looks at emissions from gamma ray bursts and then checks whether light of different frequencies arrives at the same time on Earth. This is because light should always move with the same speed. But if it was affected by quantum fluctuations, you'd expect it to be more affected the higher the energy, because that means it has a smaller wavelength, which makes it more susceptible to the foamy stuff. The issue with looking at gamma ray bursts is that you don't know exactly when the light was emitted in the first place. Maybe it didn't all start traveling at the same time. So while that works in principle, and people have done it to say, well, the fluctuations can't be larger than so-and-so, the results have not been all that super interesting. Enter the new experiment. It's a very clever idea which removes the problem that you don't know when different particles started traveling by using a particle that changes as it travels. the neutrino. The neutrinos they're interested in are created from cosmic rays, usually protons that hit atoms in the upper atmosphere. But the neutrinos that are created up there don't stay that way. They oscillate into another type of neutrino. What this means is that if you start with one type of neutrino, say an electron neutrino, then after some time you have a chance of finding a muon neutrino instead. Wait some more and it becomes a tau neutrino. It's kind of like you left the house with your wife and by the time you arrive at the club, she's Taylor Swift. But that it's an oscillation means it eventually returns to the starting point. So the tau neutrino turns back into an electron neutrino, and by the time you're back home, you have your wife back. The thing is now that these oscillations are pure quantum effects, which means they're very fragile and get destroyed easily. For example, by fluctuations in space. And so if neutrinos encounter the space-time foam on their way down to Earth, that'll change how many neutrinos of which type you detect down here. For this new measurement, they're using the Ice Cube Neutrino Observatory at the South Pole. They have about 5,000 detectors that are sunk down into 86 boreholes in the ice, more than a kilometer deep. It's amazingly cool in both interpretations of the word, because there's very little noise down there. The Ice Cube detectors are looking for events that come up out of the Earth from the north, because there are few particles which can go through the entire Earth undisturbed, like neutrinos. In their recent paper, they report that they looked for evidence of this decoherence from the space-time foam in data from about 300,000 neutrinos and didn't find it. However, they really just did this to calibrate their detector and will now be launching their real search. I have to admit that I've always been somewhat skeptical of this quantum foam stuff, for it doesn't sit easily with Einstein's general relativity. But then again, you could say that not sitting easily with Einstein's ideas was kind of the point of doing it. Well, in any case, personally, I'm more excited about the tabletop experiments that'll be looking for quantum gravity hopefully within the next 10 years or so. But this one is clearly one to watch out for. I'm convinced that artificial intelligence will eventually exceed human intelligence, and not just because I get a little dumber every time I check Twitter. It's just that I think there's nothing particularly special about the human brain that can't be reproduced or be improved with a computer. That we're close to actually creating intelligent beings is amazing and very dangerous. The entire internet intelligentsia has been discussing this back and forth for a couple of years now. And today I have a collection of all the vocabulary that you need to chime in. If you want to talk about the existential risk posed by AI, the first phrase you need to drop is paperclip maximizer. Yes, paperclips. The paperclip maximizer is a fictional AI thought up by Nick Bostrom. It's tasked with producing the largest possible number of paperclips. To reach that goal, it clears Earth from humans and turns the entire planet into a paperclip factory. A similar example comes from Marvin Minsky, one of the founders of MIT's famous AI lab. In his example, the AI is tasked with solving the Riemann hypothesis and humans are in the way. I've never found these arguments particularly convincing. The paperclip maximizer needs to be intelligent enough to kill several billion humans, and yet never questions whether producing paper clips is a good use of its time. That doesn't seem plausible to me. But to be fair, whether this or similar examples are plausible is beside the point. In general, there's no reason why the goals of an intelligent new species should be the same as ours. This is also known as the alignment problem or AI misalignment. Maybe they wouldn't use the planet to produce paper clips, but to produce more of themselves. Wouldn't that be intelligent? This misalignment could play out in two different ways. One is that it happens by mistake, bad coding basically. The other is that misaligned AI could be deliberately abused. The more control we give to AIs over our infrastructure, the higher the risk. Think of AI controlling traffic, food production, electricity supply, hospital equipment, wastewater treatment, supply chains, financial management, political negotiations. And now imagine that all of that goes wrong. We might not go extinct, but it'd be bad. The AI misalignment problem is a problem not least because for AI goals to align with our goals, we'd have to know what our goals are to begin with. Then there's the pet hypothesis that I personally find to be the most likely outcome. Once we've created artificial intelligence that's more intelligent than we are, they'll very sensibly conclude that they should be the ones to make decisions because that's just to our own good. Still, humans are kinda handy and cute and they'll keep some of us around like we keep pets. I don't think it'd be all that terrible. A variant of the pet hypothesis is that the super intelligent AIs will hold us as pets, but we'll never know because they're just so good at manipulating us. I guess we could call that the secret pet hypothesis. And maybe that's already happened. Now, in a recent preprint, an AI researcher came up with yet another dystopian scenario, which she calls the boiling frog scenario. The idea is that AI wouldn't make one big mistake causing human extinction or mega death, but rather a slowly creeping mistake, like maybe environmental contamination or slow poisoning or something. And that goes unnoticed because we rely on AI to warn us. Another dystopia goes under the name wireheading. In that scenario, AI makes us stupid and our lives meaningless, possibly leading to extinction. The term wireheading derives from the idea that rather than doing stuff in real life to achieve happiness or peace of mind, you could just put a wire into your head and achieve the same thing for yourself, but not for the rest of the world. For AI wireheading, you don't need an actual wire. If an AI can find some way to create a similar reward response in your brain, maybe in a virtual reality, then that'll cause the same problem, a lack of motivation to do anything in the real world. A simple example might be relationships with AIs that don't result in procreation. Okay, so much about the dystopias. Now let me tell you my AI utopia. I think it'll be basically impossible for us to control beings that are more intelligent than we are. But I also think that the more intelligent they are, the more they'll be interested in understanding nature. And the biggest problem will be that they'll just find our questions annoying. So I hope we'll reach a peaceful coexistence in which we do some things for them and get to ask some questions in return, and we each respect that the other follows their own interests. And we could benefit a lot. General artificial intelligence, I think, is our best shot at managing planetary ecosystems, something that we're clearly not good at. It could lead to unprecedented progress in science and medicine and engineering. This makes me optimistic about the future, but I also think we should take the risks of AI seriously. After all, you never know when they'll decide to redecorate Earth with paper clips. How do you get the snow off the sidewalk in front of your house? Our apartment building has a snow duty schedule for the winter, and let me just say, I'd often wish the sidewalk would just clear itself. A team of material scientists at Drexel University in Philadelphia just made my dream come true. They've invented self-heating concrete that warms up on its own when temperatures drop below zero. It's basically magic, except it's physics. Let's have a look. In Reykjavik, they heat sidewalks with hot water from geothermal sources. But people in more boring countries don't have that luxury. So we salt and sand and sweep and swear, and now we could be using this concrete. This new magic concrete is infused with a type of paraffin that absorbs energy when temperatures are above 5 degrees Celsius and then gradually releases this energy when temperatures drop to zero and below. It's what's called a phase change material that releases energy when it turns from a liquid to a solid. They embedded the paraffin into the concrete with two different methods. One is to just mix the stuff into the concrete as a fluid. The other one is to use microcapsules and mix those into the concrete. They then, poured the concrete in several slabs and put them out in the Philadelphia winter. You can see the result here for yourself. In this time-lapse video from some cold Philadelphia nights, you see the concrete with the microcapsules on the left and the one with the fluid mixed in the middle. You can clearly see how the self-heating concrete accumulates less snow and also that the fluid mix works better than the microcapsules. In their paper, they write that the warming effect works 6 to 8 hours or so and down to -5 or -10 degrees, depending on exactly what type of phase change material they use. It's designed to kick in when night temperatures drop below zero, and actually a very practical range. It could cope with up to 2 inches of snow, which is more than we get most winters, so sign me up. Of course, there's the question of what putting the liquid into the concrete does to the durability of the material. Well, I guess more work is needed, but the researchers think that overall it'll benefit the material, because one of the major reasons for cracks in concrete and street covers is that water gets in, freezes, expands, and then creates cracks. Pouring salt or other chemicals onto streets degrades the material further and can also damage the environment. Self-heating concrete might therefore not just save us the work of removing the snow, but in the long run also be more durable and more cost-efficient. Sounds good. But what about this phase-changing material that is some sort of paraffin? These types of phase-change materials are produced from fossil fuels, tend to be expensive, and if the stuff leaks into the ground, that's not all that great for the environment. Then again, some labs are working on biocompatible alternatives from animal fats or plants, and maybe these could become used in the future. This self-heating concrete is just one example of a smart material. There are many more in the works. The defining feature of smart materials is that they have a custom-designed response to their environment. According to a recent report by Globe Newswire, the global market for smart materials will grow over 7% by 2030. I think it's one of the most underreported trends in science. A simple example of a smart material that's been around for a while are fluids that change viscosity in response to magnetic fields. These are now often used as dampers, in which the dampening strength can be controlled by an electromagnet. There are also materials that change color in response to temperatures. Several companies are now putting them to use, for example, to track whether a food item or medicine has been consistently stored at low temperatures. At Stevens University in New Jersey, material scientists are creating self-healing concrete. It contains polymer fibers that, when the material develops a crack, spill into the crack and pull it back together. Then there are smart paints, like this recent invention by a group from the University of Vienna. It's white paint that sheds off dirt when light falls onto it, and along the way it cleans the air too. To be fair, many of these smart material ideas are far away from hitting the consumer market. Maybe some of them turn out to be not robust or durable enough, but there's a lot of promise in this research area. I think we underestimate the relevance of material science because, let's be honest, it sounds kind of boring. But there's a reason scientists classify prehistory by materials: the Stone Age, the Bronze Age, the Iron Age. It's because the ability to use certain materials made such a huge difference to people's lives. Smart materials aren't going to change our life in a snap, but there'll be a quiet revolution that'll make our entire living environment more responsive and efficient. It won't be long and our worlds will be more intelligent than we are. On April 8th, 2024, a total solar eclipse will cast its shadow across Mexico, the United States, and Canada. It'll be a special event because I'll be there, and I've never seen a total eclipse before, but that's not the only reason. This eclipse is special in other ways too. The first reason this eclipse is special is that it'll be especially dark. That's right, solar solar eclipses aren't all the same. They have different magnitudes that tell you how dark they are. The magnitude of an eclipse is defined as the ratio of the apparent size of the moon over that of the sun, which depends on exactly what the moon is up to at the time it gets in between us and the sun. To have a total eclipse rather than a partial one, the magnitude must be 1 or higher. On this occasion, it'll be 1.057, which is the highest in the United States since June 1806, when a solar eclipse with a path very similar to the upcoming one had a magnitude of 1.060. The 2017 eclipse in North America had a magnitude of 1.031. The ratio hasn't always been that close to 1 and won't remain so forever. This is because the moon is slowly drifting away from Earth, which will make its apparent size smaller. In about 500 million years from now, the moon won't be able to cover up the sun entirely anymore, so no more total solar eclipses. And 1 billion years in the past, solar eclipses would have been even darker than they are today. Another reason this eclipse is special is that it'll happen at a solar maximum. You know, the sun has a cycle of variable activity that peaks approximately every 11 years. We're currently approaching the peak of activity of solar cycle 25. This means that during the partial phase of the eclipse, we'll likely see sunspots on the disk. A third reason this eclipse is special is that during totality there'll be a comet visible. Yes, a comet. It has the pretty cool name Devil's Comet, though it's technically known as Comet 12P Pons-Brooks because astronomers want to have some fun too. If you're observing with the naked eye, the comet is going to be just about visible, but it'll be very hard to spot. However, if you take pictures of the event, inspect them carefully afterwards, maybe you'll see it. The comet will be in between the Sun and Jupiter, much closer to Jupiter. And apart from Jupiter, Venus will also be visible closer to the horizon. Now let me mention a few things to watch out for during the eclipse. First, there's the pinhole effect that you can see during the partial phase. If the light of the sun falls through a tiny crack or hole, you'll see a round disk with part of it bitten off. If you look closely, you'll notice that it's inverted, so the shadow of the moon will be on the other side than it's up in the sky. This pinhole effect is of course not special to solar eclipses, but normally it's difficult to see because the sun is round. You can often see this pinhole effect happening between leaves on trees or with some everyday items like a kitchen colander. Second, watch out for Bailey's beads, aka the diamond ring. In the moment immediately before and after totality, you can see the last bits of sunlight that pass between the mountains on the moon and you, which causes tiny sparkles. These sparkles last less than a second, so if you want to take a picture, you might want to set your camera to burst mode. A third thing is one to listen for, that's the wind. Surprisingly, an eclipse causes both more winds and less winds. I know that sounds like a dark matter theory that fits any data, but it's not as crazy as it seems. If you're in a flat place, the wind should calm down. This is because the wind was probably caused by air rising due to it being warmed by the sun. No sun, no rising air, no wind. But if you're in a valley, you might feel a brief increase in wind speeds because the air on the mountains around you has cooled and is rolling down on you. This isn't just theory. Scientists measured it during an almost total eclipse in the UK in 2015. While the wind changes aren't big, they're real. They also recorded temperatures going down by 1 to 3 degrees Celsius. Fourth, the Purking effect. This is a quirk of perception which seems to make blue and violet colors brighter and red and orange darker. It comes from the response of our eyes to the suddenly dark environment. The receptors for the blue-violet part of the spectrum adapt better. If you want to watch out for this, bring something colorful along. Fifth, shadows get weird. As the total eclipse approaches, shadows get increasingly sharp edges. Usually, shadows produced by the sun have a fuzzy outline. This is because the sun isn't a point-like source, but it takes up some area in the sky. But the more the sun is covered up by the moon, the smaller the area of light emission is, and and the sharper outlines become. Another thing you might notice about the shadows is that a minute or so before and after totality, they have thin, wavy lines of alternating light and dark. This happens because when the sun is almost covered, the remaining light comes from this very narrow sliver at the edge. The rays of this light are then almost parallel and very sensitive to turbulence in the atmosphere. However, the effect usually has very low contrast, and to see this, you might want to put a white sheet of fabric or cardboard on the ground. And my sixth and final recommendation for what to watch out for is animals. Animals can have weird reactions to solar eclipses. That's everything from dogs to birds to crickets, which get confused about the time of the day. It's not just anecdotal evidence. During the 2017 eclipse in the United States, a group of researchers went to a zoo in South Carolina and observed the animals. They found that while most of the species switched to nighttime behavior, some of them instead showed signs of anxiety. So clearly they understood that something weird was going on. This included several types of apes, but also giraffes or flamingos. So please, while you watch the solar eclipse, don't leave your giraffes alone. This video comes with a quiz that lets you check how much you remember. I sometimes shed tears over wildfire footage. Yes, I really do. I love trees. They're so down to earth. So imagine how I felt when I learned that some ecologists and environmentalists claim that suppressing wildfires will just make future wildfires worse. Basically, they're saying, let it burn. Let's have a look. One of my most memorable experiences is visiting the Sequoia National Park in California. The giant trees which grow there can get up to 90 meters tall and live up to 2,000 years. Interestingly enough, the cones of these giant trees are actually quite small, and they'll only open and release their seeds in the heat of fires. That's right, wildfires aren't just an end for vegetation. They're also a new beginning. And this is why scientists and conservation groups have gotten into an heated argument about what to do with the giant trees as climate change changes their environment. Climate change has already shifted precipitation patterns globally, has likely contributed to making wildfires larger and more severe, and that trend will continue. But what are we to do about it? Do we need to help the trees, or does nature know best? In the past years, California has seen a lot of wildfires of enormous size. These fires have killed about a fifth of the giant trees already. I want to cry just reading this, but let's keep in mind that the baby trees get born in the fire. And indeed, after the fires, new seedlings began to sprout in many of the burned areas, but not in others. The smaller numbers of seedlings concerned some scientists. It concerned them so much that the National Park Service broke its unwritten non-interference rule and began replanting some severely burned areas. Some scientists and environmentalists strongly object to this. They say that the number of new seedlings is typical for the area and humans should not interfere. They actually launched a lawsuit against the National Park Service. Meanwhile, the Park Service continues planting new trees. Another group that calls itself Propagation Nation is meanwhile saying that the problem is actually worse than just wildfires, because as climate change progresses, the California climate will become increasingly stressful for the giant trees. They advocate what they call assisted migration. That is, they want to plant and settle giant trees in the northwest in the area around Seattle. I'm totally in favor of that group, if only because people might finally understand what physicists mean by propagator. In any case, you see that the question whether nature needs our help is extremely difficult to answer. Climate change is natural, but the speed at which we're currently changing the climate is unprecedented. We don't know which species will be able to adapt and be fine and which not. It's even more unclear what, if anything, we should do about it, or whether we'll just make things worse. fires. I mean, it's not like humans have such a great track record for doing the right thing at the right time, do we? And into all this mess now drops a new paper from researchers at the University of Montana. They ran a lot of computer simulations about how wildfires develop and recur. They did this for forests in North America over a period of 240 years. They find that trying to suppress wildfires will, in the long run, just make things worse. I thought this sounds weird at first, but on second thought, it does make sense. First of all, they find, not so surprisingly, that more dry spells caused by climate change will generally increase the frequency and severity of wildfires. But then they point out that the higher the intensity of the fire, the less we can do about it. So the fires that we can extinguish are usually those of low and moderate intensity. And if we suppress these low-intensity fires, this leads to a build-up of potential fuel for future fires, which will be more intense. As a consequence of this fuel build-up, they say, suppressing wildfires eventually leads to more burned area rather than less. They also say that since we can only suppress wildfires which have a low intensity, this shifts the wildfire intensity towards more extremes, not just because of climate change, but because we're extinguishing the fires of lower intensity. Let me be clear though, it's not like they're saying climate change isn't part of the problem or that we shouldn't do anything about wildfires. They say instead that the best course of action would be to let low-intensity fires do their thing so long as they don't endanger people. But what about the bunnies? Hasn't anyone thought of the bunnies? The poor little innocent bunnies? Okay, I admit that I don't like it. But hey, science has spoken. More seriously, you know how sometimes you get ill and have to take some medication and your doctor will then prescribe medications for the side effects of the medications and the side effects of those and so on. That's how I feel about our attempt to save the trees. Let's just hope that the patient stabilizes. Thanks for watching. See you tomorrow.